What if we took exactly 1 kilogram of each of the 118 elements on the periodic table and stacked them, one on top of the other, on the same spot on the floor? Sounds like a question a 7-year-old would ask. But it hides one of the most interesting problems in chemistry. What happens when you force close contact between materials nature would never put next to each other? Some of these elements will vanish from your hand in seconds. Others will kill you before you finish stacking. One of them is so dense that gravity alone would make it sink straight through concrete. And at least one exists, officially, for less time than it took you to read this sentence. Let's stack the impossible, element by element, and actually understand why each one behaves the way it does. 3 rules before we start. First, every element goes in at exactly 1 kilogram, in whatever state it naturally exists in at room temperature, because mass alone changes everything. A kilogram of gas and a kilogram of solid metal take up wildly different amounts of space, and that difference is exactly what's going to decide whether our tower looks elegant or ridiculous. Second rule, we're not going to pretend nothing bad happens when we mix incompatible elements. If something explodes, leaks, or evaporates, the camera stays rolling. Third, the order we stack in matters, because in chemistry, much like in a lot of human relationships, proximity without compatibility rarely ends well. Let's start with element number 1, hydrogen. It's, by a wide margin, the simplest and lightest atom in the entire universe. Just 1 proton and 1 electron, barely any mass at all. And that extreme lightness creates our first problem. 1 kilogram of hydrogen gas, at normal atmospheric pressure, takes up around 11,000 liters. That's a balloon the size of an entire apartment room. In other words, the first brick of our tower doesn't stack anything. It just floats straight up and hits the ceiling, like someone who shows up way too early to a party that hasn't even started yet. Now compare that to osmium, the densest element found in nature. Density comes down to how tightly atoms pack together. And in osmium, the atoms lock into an extremely efficient arrangement with almost no empty space between them. The result? That same 1 kilogram, but of osmium, fits entirely inside a cube smaller than a dice. It's chemical proof that density was never about how much space you take up. It's about how tightly you've got your act together on the inside. We drop down a row on the periodic table and land on the alkali metals, the most reactive family among all metals. We place 1 kilogram of lithium at the base of our tower. It's soft enough to cut with a butter knife, and it slowly reacts with moisture in the air, forming a thin white coating. The explanation is its single outer electron. It is absolutely desperate to get rid of that electron and bond with anything willing to take it off its hands. That one loose electron is going to define the entire personality of this family of elements from here on out. Next up, pure sodium. And here, reactivity jumps noticeably. Sodium's loose electron sits in an outer shell that's farther from the nucleus, which makes it even easier to shed. And that's exactly why sodium is far more explosive in water than lithium. Just the moisture from your own breath on a humid day is enough to make it start throwing sparks. If chemistry had an etiquette manual, sodium would be that relative who confuses intimacy with volume. It reacts strongly to even the lightest contact. Dropping one more row, we reach potassium. The pattern repeats and gets more extreme. The farther that outer electron sits from the nucleus, the easier it is to lose and the more violent the reaction. A single drop of water is enough to make potassium ignite instantly, with flames that burn a distinctive purple from the excited electrons releasing energy. In our stack, potassium is living proof that in chemistry, just a little drop is never a reassuring phrase. After all that reactivity, a breather, literally. Helium, neon, argon, krypton, xenon, and radon make up the noble gases, and the name isn't an accident. Unlike sodium and potassium, these elements are already born with a complete outer electron shell, nothing missing, nothing extra. They simply have no chemical reason to react with anything. It's the one family on the periodic table whose entire personality trait is self-sufficiency. They know exactly who they are and don't need anyone else to feel complete. On the opposite side of the table, we've got the halogens. And fluorine is the most reactive element that exists, period. While sodium and potassium have one electron too many, fluorine has the exact opposite problem. It's missing just one electron to complete its outer shell. That almost complete state makes it obsessed with stealing electrons from any neighboring atom, including the glass container trying to hold it, which it slowly eats through. In other words, fluorine is the one element in our stack whose instability comes not from having too much, but from being one thing short. Just below fluorine on the table sits chlorine, the same element behind that familiar pool smell. It follows the same logic as fluorine, missing one electron to complete its shell, but since that electron sits farther from the nucleus, the pull is a little less desperate. 1 kilogram of pure chlorine forms a heavy yellow-green gas cloud that sinks and spreads along the floor instead of rising. Think of it as fluorine's slightly more self-controlled cousin. Still, absolutely not something you want to breathe up close. After so much hostile chemistry, we finally reached the crowd favorite, gold. What makes gold so desirable isn't just its looks, it's near-total chemical stability. Its electrons are arranged in a way that barely reacts with oxygen, water, or most acids, which means a piece of gold can survive centuries without rusting, tarnishing, or breaking down. 1 kilogram forms a cube roughly the size of a golf ball, small enough to fit in your palm, valuable enough to buy a house. Solid proof that, in the end, staying unchanged has always been sexier than being common. Right next to the gold, we place platinum, technically rarer in the Earth's crust, denser, and even more resistant to corrosion. It's used in catalytic converters, medical equipment, and top-tier jewelry precisely because it survives conditions that would destroy other metals. And yet, historically, it never earned the same cultural obsession that gold did. A pretty solid reminder that, in chemistry and outside of it, being technically superior has never been a guarantee of being more desired. Now a serious logistics problem. Mercury, the only metal that's liquid at room temperature. That happens because the bonds between its atoms are too weak to hold a rigid solid shape at this temperature. In practice, 1 kilogram of mercury simply refuses to stack. It runs, pools into silver puddles, and breaks into nearly perfect droplets that roll around on their own thanks to extremely high surface tension. Trying to stack mercury is basically trying to stack water, except this particular water attacks your nervous system if you breathe its vapor. Lead comes in as one of the few genuinely calm elements in this part of the stack. Dense, dull gray, and chemically low-key, it makes up for its lack of personality, with one very useful property. Its atoms are so heavy and tightly packed that they absorb radiation efficiently, which is why it's still used in X-ray aprons and nuclear shielding to this day. After so much chemical drama in the previous scenes, it's almost comforting to have one element whose entire job description is stand still and block everyone else's problem. Now uranium enters the stack. Its atoms are so heavy that the nucleus becomes unstable, slowly releasing energy through a process called radioactive decay. 1 kilogram of natural uranium isn't enough to start a chain reaction. That would require a much higher concentration of one specific isotope, but it's more than enough to send any Geiger counter into a frenzy from several meters away. From this point on, our impossible tower officially stops being something you'd want to visit without protective gear. If uranium is already concerning, polonium is a completely different level of problem. It decays much faster than uranium, releasing alpha particles at an extremely high rate. Enough that an amount smaller than a grain of salt can be lethal if ingested, as tragically demonstrated in the 2006 poisoning of former Russian agent Alexander Litvinenko. A full kilogram of polonium is, without exaggeration, one of the most dangerous quantities of matter humanity has ever managed to isolate. This is where our stack stops being a fun thought experiment and becomes, quite literally, an exclusion zone. Moving further up the periodic table, we reach technetium. the first artificially synthesized element in history, created in 1937. It barely exists in nature because every one of its isotopes is unstable, decaying before it can accumulate in any meaningful quantity in the Earth's crust. Putting 1 kilogram of it in our stack means that, slowly, it's going to transform into a different element right under our noses, which is, frankly, a fairly elegant way of saying it's permanently in the process of becoming someone else. Plutonium enters carrying an enormous historical weight. It was the fuel behind the bomb dropped on Nagasaki in 1945. Scientifically, it's fascinating for a very specific reason. It's one of the few elements capable of sustaining an efficient chain fission reaction, which made it central to both nuclear weapons and power-generating reactors. 1 kilogram of it, sitting alone here in our tower, stays faintly warm to the touch from its own radioactivity. A physical, tangible reminder that the same reaction capable of lighting up entire cities was also used to erase them. And now, the absolute top of the periodic table. Elements like rutherfordium, flerovium, and oganesson. They're created artificially in particle accelerators by slamming atomic nuclei together at speeds close to light in the hope that a few of them fuse and, for an instant, form a brand new atom. Oganesson, the heaviest element ever synthesized, has a half-life measured in fractions of a millisecond before it fully decays. Technically, it's impossible to gather 1 kilogram of it. Humanity, across the entire history of nuclear physics, has probably produced fewer atoms of oganesson than there are grains of sand in a teaspoon. If, by some miracle of physics, we could stack 1 kilogram of each of the 118 elements without anything exploding, leaking, corroding, or evaporating out the window, the entire tower would stand just over 3 meters tall, but it would weigh more than a small car, packed into a space smaller than a closet. And it would be, without any exaggeration, one of the most physically unstable, chemically hostile objects ever deliberately assembled in one single spot on the planet. An accidental monument to everything matter is capable of doing the moment nobody enforces the rules of good neighborly behavior. And of course, a tower like this would never stay standing for long. The sheer weight of the structure, combined with heat released by the radioactive elements and slow corrosion from the reactive gases at the base, would make collapse just a matter of time. And when it finally happened, every element would behave exactly the way we described throughout the video. The alkali metals catching fire the moment they meet any moisture in the air, the corrosive gases escaping in clouds, the mercury scattering into puddles, and the heaviest element simply, silently sinking through everything else. At the end of the day, this impossible stack reveals something real about how matter actually works. Mass was never about size. It's about internal organization. Hydrogen needs an entire room to exist because its atoms barely touch each other. Osmium fits inside a dice because its atoms leave absolutely no wasted space. And maybe the strangest lesson in all of this is that the entire universe, from the lightest gases to the densest metals, runs on one simple rule. How much space you take up matters a lot less than how tightly you're put together on the inside. That was just one impossible stack. There's a lot more impossible stuff for us to build, blow up, and take apart together. Subscribe, hit the bell, and let me know in the comments. What impossible question do you want us to break down? Element by element? Next!